Okay, so we already covered, hi everyone. I'm recording, yes. Okay, good afternoon everyone, Dr. Nat here. So we are doing chapter 7 today. We have previously talked about chapter 6 last week, and you had your assignment last week as well. So hopefully everyone has completed that assignment. I believe there were 15 questions, no calculations, everything. The answers all could be found on the PDF. So if you read the PDF, you should get the answer. Okay, so this is chapter 7, which is about input-output. Typically, we would abbreviate this as I/O. We have seen I/O a lot now. We have seen I/O in interrupts. We have seen I/O in chapter 2, where we discuss about interfaces, about buses. In chapter 3, so I/O, it's not something that is new. We have seen I/O a lot of times up to this point. So today, this chapter is dedicated to I/O specifically. So if you have any questions, you can feel free to ask me. You can unmute yourself, okay? So I'm going to continue because I can't see your face, so I don't know your reactions. So this is a generic model of an I/O module. Feels very weird because we have been having physical class. So this is a generic model of an I/O module. So here you have your I/O module, which we have not discussed what is the inside of the I/O module, but you can see that the outside we have links to peripheral devices, which is basically your printers, your keyboards. Those are your peripheral devices. You can also categorize CD-ROMs as your peripheral devices as well. Anything that is external to the computer is considered your peripheral devices, something that you have to attach. And then the I/O module is connected to a system bus, which, where my face is blocking. So this is your system bus. Your system bus is supposed to be connecting the I/O modules to other modules, such as the CPU module, the memory module, which we have seen in chapter 2 before. So the I/O module is connected to a system bus, where the system bus comprises of an address line, okay, address lines, data lines, and also control lines. Okay, and we have discussed this in our chapter on buses as well. So this is not the main focus here. So what I want to highlight here is that the I/O has two sides to it. The I/O module has two sides to it. One is the system bus and one that links to the peripheral devices. Okay, so bear that in mind for now. Okay, so external devices. Now we are talking about the external devices over here that is linked to the I/O module. Okay, so external devices, I/O operations provide a means of exchanging data between the external environment and the computer. So the I/O module helps to become somewhat like a bridge between the computer and also the devices, the external devices. So attached to the computer by a link to an I/O module. So external devices are attached to the computer by a link to the I/O module over here. So we have a link going on here. This is our external devices connected to the I/O module. The I/O module connects us to the computer. Okay, so peripheral device is your external device connected to an I/O module. So there are three categories of external devices. The first one is being human readable. Second is machine readable, and we have communication. So for human readable, it is designed for us to use it for the end user to understand what is going on. So such as printers, we can set it, we know what's going on, we can read what's going on. And then we have something that is machine readable, whereby the data that is captured by this machine, we don't really have a way of interpreting it unless we do this some sort of processing inside the computer. So machine readable, you get like in binary data. Obviously, we can't read that. So this is suitable for communicating with equipment such as sensors. And then for communication, you have your communication via Bluetooth. You have your AirDrop if you're using the Apple system. So that is a communication, and it is also considered an external device. Okay, suitable for communicating with remote devices such as phones or other computers. You have your Bluetooth and your AirDrop situation going on. Okay, so this is a block diagram of an external device. So remember, you had your I/O module, and we had some links going on to the peripheral device. So this is your external device that they are going to discuss here. Okay, so for your external device, you have your control logic, your transducer, and your buffer over here. You have your control signals from the I/O module, status signal from the I/O module, data bits to and from the I/O module. As I drew over here, we have the I/O module up here. We have links going on, but we did not define what the links are. So here they are telling us the links are control, status, and data bits to and from. So here you have a bidirectional line. Here it is unidirectional. So the control is given by the I/O module to the control logic, and the control logic updates the I/O module with the status. Whereas the data, you have data transfer back and forth. So the data goes through a buffer. Sometimes, okay, I will explain what the buffer is for. So the buffer is here to basically acts like a temporary storage. We know this. Briefly, we know that the buffer acts like a temporary storage. And then we have the transducer to translate the signal. So let's say I am connecting a keyboard to the I/O module, let's say. So I am pressing some keys, right? Like that. So when I press, you have some electronic signal going on, and the transducer will translate this into codes. I am pressing on the keyboard that is transmitted as an electronic signal, and that electronic signal is translated as codes. Okay, and the codes is the electronic signal is converted by the transducer to become codes, and the codes are stored in the buffer temporarily. Now, why do we need to have a place for temporary storage? Because the data rate where the keyboard can transmit or receive is slower than the I/O module can transmit or receive. So sometimes when you have that mismatch, you need a place to hold something so that they can transfer at the specified rate. So let's say my keyboard is super slow, so I store everything in the buffer first, and then when everything is ready, I transmit at the data rate that the I/O module can use. Okay, so the buffer helps to counter the mismatch, basically. Okay. So if you have any questions, feel free to unmute yourself and ask your question. Okay, so we were talking about the keyboard just now. So keyboard / monitor, they are not basically the same thing, obviously, but they are both external devices or can be categorized as peripheral device. So it is the most common means of computer and user interaction. User provides input through the keyboard. The monitor displays data provided by the computer. Now, the way that the keyboard and monitor is designed, I, as the user, give input to the keyboard in the form of typing, and the monitor gives out output to me as the user, right? The output gives out output to the user. The user gives input over here. So they are both peripheral devices, but they are unique in the sense that the keyboard receives input from the user, whereas the monitor gives out output to the user. Okay, but they are both categorized as peripheral device. So user provides input through the keyboard. The monitor displays data provided by the computer. Now, the keyboard code, what happens when a user depresses a key on a keyboard? Depresses means you press on the key lah, okay? So there are two types of things that will happen, things that will happen when you press on the keyboard. The first one is printable, which is alphabetic, numeric, and special characters. This is what we all know, what we're seeing on the screen right now. Those are printable. And then we have control, meaning to say I'm using my keyboard, which has a trackpad, and I'm basically controlling my mouse and I'm clicking on something. I don't necessarily see alphabet or numerical numbers or special characters. I'm not seeing that, but I am controlling. So that is another character. It is considered a character, but the character is a control type. So have to do with controlling the printer the printing or displaying of characters. Example is carriage return. Carriage return is like you want to go to the top of the page, you insert a break, or you want to, sorry, you don't insert a break if you want to go to the top of the page. You insert a break in the page in Word and you go to the next page, right? So those are like carriage returns. Those are the types of control that you can do, but you don't necessarily see them as alphabets, numerical, or special characters. And then other control characters are concerned with communication procedures. Excuse me. Okay, so we talked about the I/O module. We talked about the external device. The external device has a control logic, a buffer, and a transducer. The transducer helps to translate. The buffer acts as a temporary storage to counter the mismatch. You have 3 lines from here: control, status, and data bit. And then we have your I/O module. And then you have your user type of external device over here, which is such as the keyboard. This is just an example. And then you have another external device connected to the I/O module. Of course, this is also a peripheral device, so you would have the same type of, you would still basically have this. You would still have this kind of structure. Now, this should not be external device. This should be like input. And this should be your output. Remember, we were talking about the monitor and the keyboard, and this should be one way, okay? And this should be one way, okay? So it's not bidirectional, but it depends on your device that you are connecting to your I/O module. If it is bidirectional, then it would be bidirectional. But in this case, the keyboard only allows input and the monitor only allows output, okay? So when a user depresses a key, it generates an electronic signal, which I mentioned to you earlier, that is interpreted by the transducer. Okay, let me make this nicer. It is interpreted by the transducer over here and in the keyboard and translated into the 7-bit pattern of the corresponding IRA code. So the code that is generated is called IRA. This bit pattern is transmitted to the I/O module in the computer. On output, IRA code characters are transmitted to an external device from the I/O module. So for the monitor, you have your output going on and it is transmitted to the from the I/O module to the peripheral device. The transducer interprets the code. Of course, you also have a transducer over here and a buffer and also a control logic similar to this guy over here, which is the keyboard. So it is exactly the same, only the difference would be the data to and from the environment, whether it's going to be bidirectional, it's going in or going out. The transducer interprets the code and sends the required electronic signals to the output device. So the transducer interprets the code that is received from the I/O module, it translates, and then it displays what is needed to display on the monitor, what you have on your monitor, okay? To display the indicated character or perform the requested control function on monitor, okay? So I would have control, status, and this is going to be your data, status and control. So it would be exactly the same. The difference would be in the data. Okay, moving on. Okay, so what are the major functions of an I/O module? So we have over here, first, the error detection, detects and reports transmission errors. Number 2 is data buffering. So you have seen that we have the buffer and the transducer. So, and then we have the device communication, involves command, status, information, and data. And then you have your processor communication, involves command decoding, data status reporting, address recognition. Now, the difference between processor communication and device communication is that processor communication requires address recognition, whereas device communication only involves command, status, information, and data. Processor communication does that as well, and in addition with address recognition. So processor is highly complex, so it does something extra, right? And then you have your control and timing, coordinates the flow of traffic. Like I mentioned to you before, the peripheral devices are typically very slow. So you have your buffer to help counter that mismatch. Coordinates the flow of traffic between internal resources and external devices. So control timing. So we have 1, 2, 3, 4, and 5 over here. Okay. So how does the I/O module do the error detection? I think I wrote it somewhere. I don't think it's here. So data coming from the main memory are sent to an I/O module in rapid burst. The data are buffered in the I/O module and then sent to the peripheral device at its data rate. Like I told you before, sometimes our device is very slow, so we store the information in the buffer, or vice versa. Sometimes our I/O module is too fast for our devices to respond, so it goes into the buffer first. When the device, such as the printer, which is super slow, is ready to respond, then only the I/O module would transfer that. Okay, in the opposite direction, data are buffered so as to not tie up memory in a slow transfer operation. So this is basically a detailed explanation of what I told you earlier. So similarly, if the I/O device operates at a rate higher than the memory access rate, then the I/O module performs the needed buffering operation. Okay, so that is your buffer operation. Okay, so this is now the I/O module structure. Previously, we were talking about the external device having the buffer, and the external device was connected to the I/O module. By 3 lines, we had the control, status, and data. Now, the I/O module structure has, over here, we have the data line, the address line, and the control line. And this is the interface to the system bus. Okay, so this is your system bus basically. Okay, let's go back and try to relate this. We have the data, address line, and control line. Let's go back to the first slide. You have your data, address line, and control line. So basically it's the same, but it looks different. So don't get confused. This is exactly the same. So this is your system bus. In the slide just now, they just said system bus interface, and they had lines like this. Okay, so it's just a different diagram, but it's the same thing. Okay, let's go back to that. Oops. Okay, so this is the one that we talked about, the system bus interface. And then we have the interface to external device. We have our data. We have our data, which is a bidirectional line. We have our status coming in from the device, right? And our I/O module obviously will control the device. So this is also the same as the one that we have seen before. Let's go back. Okay, so here you have this is your external device. You have your control, status, and data. Okay. So hopefully you don't treat this as like separate entity, because they are the same. It's just like now we are discussing the I/O module structure. Okay. Okay, so now we can see that we have a data register, we have status/control register, and these two registers are connected to the data lines, which are bidirectional as well. And then we have our address line and control line connected to the I/O logic. The I/O logic is basically connected to everyone because it does the logic thing. It's like the brain. And the I/O logic is also connected to the external device interface, whereby this interface connects with the printer, keyboards, etc., your peripheral devices. So you can connect a lot of peripheral devices, and each one will have their own data, status, and control lines. Okay, so what you need to remember is that you have your interface system bus, you have your interface to external device. You need to remember what is your system bus, what are the lines of the system bus that is connected to the I/O module, what are the lines of the peripheral devices that is connected to your external device interface, and you have your I/O logic connected to these two registers. These two registers are connected to your data line, and your everything else is connected to the I/O logic. Okay, so basically you have to remember this diagram. Okay, So I/O operations, there are three techniques that we can do, which is first one is programmed I/O. The second one is interrupt-driven I/O. And then we have the direct memory access I/O operation. So programmed I/O, data are exchanged between the processor and the I/O module. So let's try to draw the I/O module, and we know that it is connected to your device. Don't know how many. And then we know that we have some system bus going on here. Basically, system bus connects to the memory module and the CPU module, right? But this is like a really bad drawing. So let me just erase that. That was like futile effort. Okay, so data exchange between the processor and the I/O module. Processor execute a program that gives it direct control of the I/O operation. When the processor issues a command, it must wait until the I/O operation is complete. We will see a flowchart after this and see how this impacts the processor. If the processor is faster than the I/O module, this is a wasteful processor time, of course. If the processor issues a command and has to wait until the I/O operation is done, then the processor has to pause until everything is done, when the time could be used to do other instructions. We have seen this in multiple interrupts, right? And then because of that, you have another technique or an alternative technique called the interrupt-driven I/O, which aims to maximize the processor capacity, or like the processor does not have to wait. So the processor issues an I/O command, continues to execute other instructions. It doesn't remain idle and is interrupted by the I/O module when the latter has completed its work, which is great. But everything still has to go through the processor, which is okay, but it still uses a lot of the processor's time. So another technique, which is an alternative technique to the interrupt-driven I/O, is the direct memory access, called DMA. The I/O module and the main memory exchange directly without the processor involvement. So let's say the processor issues an I/O command. The I/O command is directly triggered the DMA module, and the DMA module will execute whatever data transfer is necessary. And when it is done, it tells the processor, hey, I'm done. You can take back the operation. And the processor is only involved in the beginning and the end. And we will talk more on these in detail because this is what makes this chapter. So let's go for programmed I/O first. Okay, so here is a summary of the I/O techniques. We have our programmed I/O. Programmed I/O does not have any interrupts. It is an I/O to memory transfer through the processor. Everything must go through the processor, and the processor has to wait. And then we have the second one. This was the first one that we talked about. And then this is the second one, which is the interrupt-driven I/O, which uses interrupt. The processor does not have to wait. It can issue a command and go do other stuff. But when the interrupt is done, it has to still go through the processor, and the processor has to execute the next command. And then we have the DMA, which is a direct I/O to memory. It does not go through the processor like the other two techniques. And yes, it does use the use of interrupts, but in this time, the DMA is the one triggering the interrupt. Okay. Okay, so there are 4 types of I/O commands that an I/O module may receive when it is addressed by the processor. So the processor will issue a command and the I/O will respond accordingly. So the first one is control, is used to activate the peripheral and tell it what to do. Number 2 is to test. Are you okay? So it seems like I'm not the only one who is sick. Who unmuted? I can't see.
You can continue, Doctor.
Okay. Do you have any question? Tak ada. Okay.
No, Doctor, sampai.
All right. Let me see. This one. Okay. Okay, so the second one is test, used to test various status conditions associated with the IO module. For example, the printer is super slow, as we talked about just now. So I need to test whether the printer is ready or not. So I'm going to send a test line, sorry, a test command. Hey, are you ready to receive? Or hey, are you turned on? So those are the types of tests that can be done. And when you have verified that the printer is ready or the printer is on, then only you can start control, right? If you are controlling without knowing what the status is, there's no point. So that is the status line 4. Okay, and then we have the read, causes the IO module to obtain an item of data from the peripheral and place it in the internal buffer or the data register. And then we have the write, to take an item of data from the data bus and transmit that data item to the peripheral. Of course, we are writing onto like a CD-ROM, or we are writing onto a USB drive or a hard disk. So what you do is you take the data item from the bus and transfer it to the peripheral. For the case of reading, we want to read from the USB drive or from the hard disk and you place it into the internal buffer before it goes into the bus. Okay. Okay, so let's take a 7-minute break. Let's come back at 2:38. Okay, so I'll see you at 2:38. Okay, so I am back. Hopefully you are back as well. Don't sleep, wake up. Okay, let's continue. So there are 3 techniques for input of a block of data. So just now, what were we talking about? We were talking about the IO commands. So now we are going to talk about the 3 techniques that we have discussed in this slide over here. Let me go back. Oh, sorry, not this one. This one, the IO operations. There are 3 techniques that are possible for the IO operation. You have your program, your interrupt, and your direct memory access. So now let's look at the flow chart. We know that the program IO wastes the processor's time. The interrupt-driven IO counters this issue, but everything still needs to go through the processor. And then we have the DMA, which is a direct from the IO to the memory. Okay, so going back to the flow chart, let's see. Where is our flow chart? Okay, it's here. So the first one over here is our programmed IO example. Our B is interrupt-driven IO, and then we have our direct memory access. So let's talk about the program IO flowchart now. Okay, so we have our processor issuing a read command to the IO module. So basically, we want to read whatever that is on our peripheral device. For example, you want to read your phone, you connect it, and your processor issues a read command to the IO module, telling the IO module, I want to read from this phone. So what it does is the CPU sends a read command to the IO. What the IO does is it reads the status of the IO module first, and then checks status. If the IO module is ready, then it goes to the process of reading. If it is not ready, it goes back to over here. And then the IO module will report back on the status again. The IO module basically looks at the status of the peripheral device. If the peripheral device is not ready, then the IO module also tells the CPU, hey, I'm also not ready. So what happens? Not ready, go back over here. Not ready, go back over here. Not ready, go back over here. So it wastes the processor's time. And then when the peripheral device is ready, the IO module tests again, and the processor, the IO module receives a good status condition, and then only the IO module can report a good status to the CPU as well. So now it is ready to do the reading. So read word from IO module, and then write word into the memory. And if it is done, then you can go for the next instruction. If it is not done, then you have to go back and do more reading. Basically, if you want to read a large amount of data, so you would have to do this bit by bit until it is done. Sorry, not bit by bit. What I meant is by blocks of blocks, depending on the way that it is designed to read. Okay, not bit by bit. I cannot use that word because bit means something else in this class. Okay, so if it is not done, you would go and issue the read command, and the same process happens again. If it is ready to read, then you would go for this. If it is not, then you would basically be looping around here. Not good. Okay, so that is your disadvantage, but it is very straightforward. That is the pros, but the disadvantage is wastes the processor's time and very time consuming. Okay, next one. So we are talking about the interrupt driven IO in this flowchart. So basically the processor issues a read command to the IO module. The IO module is obviously connected to the peripheral device, and the peripheral device will check, the IO module will check the peripheral device. And while the IO module is doing its thing, the processor can do something else. Good. And then the IO module is ready. It tells the IO interrupts the CPU, hey, I'm ready. The device is also ready. Let's do some checking again. And then it checks the status. And if there is any errors, do some error correction. If there is no error, proceed. Read word from the IO module, and then write the word into the memory. If it is done, then you can execute the next instruction, which is done by the processor. If this thing is not done, then you would continue reading until whatever that you want to read is done. So sometimes it takes you a large amount of time to read your phone because your phone is heavy. If your phone only has like a little bit of data, then it would not take a lot of time, right? Because there's only like a few cycles of this, maybe. Okay, So what happens here is the IO module will do its thing. It's not reported here. Basically, this is what the interaction between the processor and the IO module. What the IO module does with the peripheral device is unknown to this flowchart. If it is here, then you would have a trouble remembering it, right? So let's just focus on this one. So interrupt IO is more efficient than programmed IO because it eliminates needless waiting. However, interrupt IO still consumes a lot of processor time, because every word of data that goes from memory to IO module or from IO module to memory must pass through the processor. So everything has to still go through the processor. So the processor is basically always busy. Okay, so here is some explanation from the point of view of the IO module, and then we have from the processor's point of view. So the IO module receives a read command from the processor. Over here, it was from the CPU, right? The CPU issues a command. The IO module receives a read command from the processor. The IO module then proceeds to read data from an associated peripheral. So once the data are in the module's data register, of course, the data will go through the buffer or the data register. The module signals an interrupt to the processor over a control line. Okay, the module then waits until the data are requested by the processor. Basically, when it interrupts the processor will finish executing whatever business that it's currently doing. And then when that cycle is done, it will respond to the interrupt. So this is what it means when the module waits until the data requested by the processor. So when the request is made, the module places its data on the data bus and is then ready for another IO operation. So when the processor has completed the cycle of whatever instruction that it was doing, it responds to the interrupt and lets the IO module know that it is ready. So the IO module will place the data requested on the data bus. Remember, our IO module is connected to a system bus that has data control and address line, right? So from the processor's point of view, the processor issues a read command, okay? It then goes off and does something else. For example, the processor may be working on several different programs at the same time. At the end of each instruction cycle, the processor checks for interrupts. So it is doing some other instruction and it will consistently check for interrupt. If there is an interrupt, then it will receive that interrupt. But even though it knows there is an interrupt, it will finish its business first. Okay. When the interrupt from the IO module occurs, the processor saves the context of the current program and processes the interrupt. We have seen this in interrupt chapter 3. Whatever that it was doing, it saves so that it can return back to the user program after it has finished processing the interrupt. So in this case, the processor reads the word of data from the IO module and stores it in memory. Okay, and then it resumes execution. So why was that necessary to know? Because we will look at the user program in the interrupt point of view later. Sorry. So hopefully this text will help you to digest things better. I want you to understand it. It's not supposed to be memorized because if you memorize, there's too much to memorize. Okay. Make sure you can elaborate it in your own words. So that's how you try to remember things in this class. Okay. And then your last one, the last IO technique is the direct memory access, bypassing the processor. So what it does is the processor issues a read command. This is the CPU issuing a read command to the DMA module, and the CPU goes do something else. So what the DMA module does is that it does whatever the necessary data transfer. Read status of DMA module only happens when the DMA interrupts the processor again when it is done. The DMA interrupts the processor when it is done, and then the processor reads the DMA module, and then the processor continues with its next instruction. So very versatile. the processor is freed up, it's not always busy, and that is good for our machine or for our laptop. So when the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and the end of the transfer. Okay. Okay, so we talked about the 3 I/O operation techniques. There were 3 programmed. We had, what was it? Program interrupt-driven I/O and also DMA. Now, for programmed I/O, we have 2 types of mapping. Okay, 2 types of mapping. We have the first one called a memory mapped I/O. The second one is isolated I/O. Now, what I want you to know here is that for the memory mapped I/O, you only have a single address space, a single one, for both the memory location and I/O devices. Basically, you know that we have your memory register, and then for one of this, it contains both address of memory and I/O device. So the processor treats the status and data registers of I/O modules as memory locations, of course, because basically it is a memory location, and uses the same machine instructions to access both memory and I/O device, because this one line tells you the memory and also the I/O device. So for example, if you have 10 address line, a combined total of 2 to the power of 10 gives you 1024 memory location and I/O addresses combined. Okay, so the advantage to this is you can have more efficient programming, because you can have more instructions encoded in your address. However, the disadvantage is that you are using a lot of memory address space. How do I say this? Because you are combining onto a single line, so it becomes very lengthy. Okay, so you are not very, you can make it complex, but at the same time, you are reducing space for other memory. Okay, and then you have your isolated I/O, whereby your read line and write line are separated. That is why it's called isolated. So a single read line and single write line are needed on the bus. The command line specifies whether the address refers to a memory location or an I/O device. Now it's no longer combined, it's no longer complex. It's very straightforward. The commands are limited. Okay, so again, with 10 address lines, now you have 1024 memory location and 1024 I/O addresses. So you have more memory. Because of the address space for I/O is isolated, this is referred to as isolated I/O. Now, to summarize these 2 mapping summaries, this is specifically for programmed I/O. If I ask you, the 2 mapping summaries which are memory mapped and isolated I/O belong to which I/O operation technique? You should be able to know this, okay? So only for programmed I/O, not for interrupt, not for DMA, programmed I/O only. You have your memory mapped and your isolated I/O. Memory mapped combines the address and also the memory device and memory shared address space. Isolated separates these 2. And then you have limited set of command. The command for memory map can be made very, very detailed or very complex and very special. Okay, so those are the 2 differences. Okay, so this is for interrupt processing. Just now we talked about the programmed I/O. The programmed I/O has 2 mapped memory mapping. And then we are talking about the second technique, which is the I/O interrupt-driven I/O. So how is the interrupt-driven I/O executed? So let's talk about that. So the processor finishes the current instruction before responding to the interrupt, like I told you before. Now, whenever that it issues a command and it goes do something else, the I/O module is processing that, whatever request that it is being requested, and when it is done, it will go to the processor and interrupts the processor. Hey, I'm done. Please look at my request. So then the processor finished the current cycle. So this is where we are at. the processor finishes the current instruction before responding to the interrupt. It knows that the interrupt has happened, but it finishes what it's currently doing. And then it tests for interrupt, determines that there is one, and sends an acknowledgement signal to the device. Even though the I/O module already told the processor that it is triggering an interrupt, right? The processor still needs to make sure that the interrupt still exists after that it has completed its instruction. So that is why it is necessary to test for an interrupt. If the interrupt is still there, you acknowledge, the processor has to acknowledge, okay, so I know that you have an interrupt and I am acknowledging your interrupt. So now the I/O module can stop the trigger or the interrupt trigger. The acknowledgement allows the device to remove its interrupt signal. Okay, so this is where it is happening. So device issues an interrupt, processor finishes execution of current instruction, processor signals acknowledgement of interrupt, therefore the device can remove its interrupt signal. And then the processor pushes program status word and PC onto control step. Why? Because before it starts to process the interrupt, it needs to know where it stopped. It is stopping its current program. It needs to know where to stop. It needs to know where it is taking a break. Remember that we had like the user program going on, and then we had an interrupt going on at, let's say, N. So the user program has to know where the break happens because it wants to go process this interrupt over here, remember? So before it goes to process this interrupt, it needs to know what the status is or where it should come back after it is done processing the interrupt. Okay, so that is your PSW and PC. PC is your program counter, if you still remember. PSW is a new term. It is your program status word. So program status word and program counter onto the control stack. And then the processor loads new PC value based on the interrupt. Let's say the interrupt happens at Y. So the processor loads the new PC to become Y. Previously, it was processing another instruction, but now it has to process the interrupt, which is happening at Y. So it loads the value Y. So we will see this later in a flow diagram. And then after that, in the software part, it saves the remainder process state information, whatever registers that it is currently working with, it will store that somewhere, and then it will continue to process the interrupt. Finally, after it has saved the PSW and PC, it has loaded the new PC value, it has saved the registers that it was currently doing before, and then only it can go for the process interrupt. So there's a lot of steps involved before the interrupt can be processed, and then restore the process state information after the interrupt has been successfully processed. So you restore the process state information. What is that? It is basically going back to these values, PSW, PC, and the registers that were saved before. So this is restoring your previous state. You can imagine it like restoring your backup file. Okay, and then restore old PSW and PC into your processor. Sorry, onto your control stack processor, basically. Okay, so let's hope for, yeah, we have it here. Okay, so now we can talk more on this. Okay, looks overwhelming, but bear with me. We will do this slowly. Hopefully everyone can focus and ask questions if you don't understand. Okay, so let's try to understand this. Okay, so I told you that when a processor is currently processing another instruction, but it receives an interrupt, right? It receives an interrupt. What happens is that it needs to finish what it is currently doing. I think I've repeated this at like 10 times. Okay, so it finishes what it's currently doing before it responds to the interrupt. Before it can even process the interrupt, what do we have to do? We have to store the PSW, the program status word. We have to store the current PC value, and we have to store whatever registers that were involved in the current instruction. or like the instruction, the last instruction that the processor was doing. Okay, so let's try to read this and see if it relates to what we learned in the previous slide. So at this point, the program counter or the PC and the program status word relating to the interrupted program have been saved on the system stack. So here, we are saving your program counter over here, PC, we are saving it here. We are saving your general registers over here. So you are saving a whole bunch over here before we start to go for the process of the interrupt. However, there is other information that is considered part of the state of the executing program, the contents of the processor registers, which I told you earlier, the general registers, because these registers may be used by the interrupt handler. So why are we saving this? Because the interrupt handler may utilize this guy. And if the interrupt handler utilizes these registers, which means that whatever data that is stored in these registers will be wiped out. So before that happens, you put it onto the control stack so that you can continue working on those data later on. Okay, so again, you are transferring your program counter, PC, PSW, and general registers onto the control stack. Okay, I hope everyone is still with me. Don't sleep on this. Okay, so in 7.7a example, a user program is interrupted after the instruction at location N. So basically, it is doing an instruction at N. Okay, let's try to remove this. Let me make this bigger. So what it is doing now, it is doing the instruction at N. And we know that we need to save the next instruction to resume our execution, right? To resume our user operation. So instead of saving it as N, which is the last instruction, you save it as N plus 1. It's not N, it's N plus 1, which is the last instruction, counter plus 1, basically the next one lah. Okay, so the contents of all the registers plus the address of the next instruction N plus 1 are pushed onto the stack. Okay, this is just repeating what we talked about just now. The stack pointer is updated to point to the new top of the stack. So the stack pointer is updated to the top of the stack, which is T, because after you have loaded your PSW, your PC, and your general registers, these things consume up until T. So you put in that value T over in the stack pointer. Okay. So this is before we process the interrupt. Okay. So any questions about this one first, before I move on to the return from interrupt? So everyone's okay? I see someone has left the lecture. One person, not sure who. Okay, so if no questions, I'm going to continue. Again, if you are too shy to ask, you can always type in your questions. Or you can just unmute yourself and ask. Okay, so here the next one is returning from the interrupt. What happens after we have processed the interrupt? So the interrupt handler processes the interrupt handler next processes the interrupt. When the interrupt processing is complete, the saved register values are retrieved from the stack. Basically, you are taking this back and putting it back into the general registers. But I'm using the wrong diagram. It's supposed to be over here. So you are taking back what you have saved and putting it back into your general registers. And then you would want to put in your N plus 1 that we saved earlier into your program counter. And then your stack pointer would be T, which is, what was it? The PC, PSW plus all the general registers up until T, right? The final act is to restore the PSW program counter values from the stack. As a result, the next instruction to be executed will be from the previously interrupted program. We executed N, now we are going for N plus 1. Note that it is important to save all state information about the interrupted program for later resumption, which I have repeated like 10 times at this point, now 11 times. Okay, so you would see that we know what n plus 1 is, we know what t is over here, and we know what our, oh, I did not tell you about y plus l. Okay, so remember I told you when it starts to process the interrupt, the PC has to load the new location of the interrupt. Okay, I told you over here. Where did I write y? Okay, processor loads new PC value based on interrupt. So instead of the PC being n plus 1, which is what the user program wants, but now it has to process the interrupt, right? So it has to go somewhere else to do this. So the PC will load the new value based on the interrupt. So in this case, the new value of interrupt is at y. So you would see that your program counter is at y plus l when it has finished the processing the interrupt. It starts at y and it finishes at y plus l. So you would see that the program counter finishes at y plus l. This is after it is done. After it is done, you would load the last instruction that the user program wants to resume, right? Which is n plus 1. So this is why n plus 1 goes into this one over here. Okay? So that is where your y comes from, which is the interrupt place. Okay, so that is it, I guess. If you understand this, shouldn't be too hard to remember. Don't try to memorize, please try to understand it. If you have any questions, you can always text me or email me or just ask me in class, okay? All right, so we have done this one. Oh, not this one yet, that is your assignment. Okay, so we have some design issues with our I/O module or I/O implementation. So two design issues arise in implementing interrupt I/O, which is the first one being, because there will be multiple I/O modules, how does the processor determine which device issued the interrupt? So basically you are connected to many peripheral devices, right? You receive an interrupt. How do you know which device issued that interrupt? And then the second issue, design issue, is if multiple interrupts happen at the same time, how does the processor decide which to process? And we have talked about this using the nested interrupt and also the sequential. Sequential, basically, you do this in order. Then the nested one is that you decide based on priority, which one is more time sensitive and so on. So again, number one is, how do you know which device issued the interrupt? The second one is, if you get multiple interrupts, which one do you process first? Okay, so those are the two design issues. Ooh, so this is very small. Okay, so let's take a 7-minute break again. Let's come back at 3:15. Okay, so if you have any questions, you can ask me now or later, it's fine. Take your break. Let's continue and finish up this chapter a bit. In a bit. Okay, so I am back. Hopefully you are back as well. Wake up if you're sleeping. This is the first class that I have people sleeping. I don't know, but it is a very lecturist class. I have to admit that. Okay, so let's continue. We were talking about that there were two design issues, right? We talked about what if there were multiple devices connected and we received an interrupt. How do we know which device issued that interrupt? And then the second one is if you have multiple interrupts, which one do you process first? So to solve the first one, we have several techniques, of course. So basically you can make like a mind map of this entire chapter, because basically you have like a lot of branches going on. You have the IO module, and then you have the mapping technique of the program IO, the three techniques of the IO module, IO operation, which is program, and then you have your interrupt driven IO, and then you have your DMA. Under the program, you have the mapping, which is the isolated and the memory mapped. And then under the interrupt driven, I think you have several of that, which we have not discussed yet. And then the DMA, we don't have so much. But the design issues, we have 4 techniques that are commonly used. The first one is multiple interrupt lines. So basically, you know that you have your module and you have your one line for control, one line for status, one line for data, etc. So that is like the general overview. But sometimes in the design, you can also like have several lines dedicated for one purpose, which is in this case, they use multiple interrupt lines between the processor and the IO module. So basically you have like all these lines that is dedicated for interrupts. So this is obviously the most straightforward approach, but we know that the most straightforward approach is not necessarily the best case because it will always be wasteful. So consequently, even if multiple lines are used, we still don't know. It is likely that each line will still have multiple IO modules attached to it, and we still don't know which is which. So this doesn't really solve anything if we have a lot of peripheral devices going on. Okay, so the next one is software pool. So again, it's like I ask you to answer a question and you tell me whether you have eaten or not. So that's your poll for today. Have you eaten your lunch? Yes or no? So the same thing happens over here. You have a software pool. The processor detects an interrupt. It branches to an interrupt service routine, whereby the service routine polls each of the IO module to determine which module causes the interrupt. So basically, if you have like 10 modules, the interrupt service routine goes to each and asks, hey, did you issue an interrupt just now? If you did, please let us know. So basically, it's quite a lot of work for the interrupt service routine. This can be done by command line test IO, where the IO module responds positively if it is the one that sets the interrupt, or the processor reads the status register of each IO module to identify the interrupting module. And again, if you have a lot, then it would be time consuming. If you have not so much, then maybe it would be fast. But again, not that ideal. It is still time consuming. But obviously, this is better than the multiple interrupt lines, because this basically does not tell you which is which. The software pool, at least you know which one is doing that. I mean, issuing the interrupt, but it takes more time. And then you have the daisy chain, which is hardware pool. This is software pool. This is hardware pool. So the interrupt acknowledged line is daisy chained through the modules. So when the processor senses an interrupt, what this means, what this line means, when the processor senses an interrupt, it sends out an interrupt acknowledge. We have seen this before. This signal propagates through a series of IO modules. So the signal goes through these guys until it gets to the requesting module. So it's not basically asking, it's transmitting a signal. The requesting module responds by placing a word on the data line. So let's say this is the IO module that sets the interrupt, that triggered the interrupt. So it would put something on the data line or the data line that is connected to the CPU. So this data line, the word that is placed on the data line is also known as a vector. What is a vector? A vector is the address of the IO module or some other unique identifier. Address of the IO module or some other unique identifier. So again, what happens is the processor acknowledges the interrupt, sends a signal that goes through all the IO modules. This is called daisy chain. And all the IO modules receives this signal, and the one that sets the interrupt responds by putting in its own address. Basically, hey, this is my number, take it. So it's telling the processor, this is my number, call me, something like that, but instead in the form of an address. Okay, so this address is called vector, and vector can be address or anything that is uniquely tied to the IO module. So it is it is typically a word. The word can be an address or a unique identifier. Okay, and then we have the vectored interrupt, whereby the processor uses the vector is your phone number, as a pointer to the appropriate device service routine. Basically, the processor takes your phone number, gives it to a third party, hey, please handle this person, he's bugging me, something like that. Okay, so it gives your phone number to the device service routine, or in this case, the address or the unique identifier or the vector, avoiding the need to execute a general interrupt service routine. Because why? The general interrupt service routine is basically a software pull, and it is time consuming. So we don't want that. So the processor doesn't want to be busy. It lets a third party do it by using a vector interrupt. Vectored interrupt, okay? The vectored interrupt is device service routine. Okay, so that is your third technique. The fourth one is your bus arbitration. We know what bus arbitration is. Basically, you control the bus. Arbitration means to control. So bus arbitration, to control the bus. So this is also vectored, meaning to say that you are using a vector. A vector is a word that can be an address of the IO module, or it can be any unique identifier. So an IO module must first gain control of the bus, because we are trying to control the bus, right? The word is bus control. The IO module must first gain control of the bus before it can raise the interrupt request line. Obviously, for us to use the bus, we must always request. And then when the processor detects the interrupt, it responds on the interrupt acknowledge line. Then the requesting module places its vector on the data line. So this is like slightly straightforward. We are using the bus to do all the communication. We don't have to like ask the, we don't have to, how do I say this? We don't have to daisy chain, okay? We use the bus. Okay, moving on. So this is an interrupt controller. Whoops. Okay, so this is an Intel 82C59A interrupt controller. So its responsibility is the management of interrupts. It accepts interrupt requests from attached modules, determines which interrupt has the highest priority. Now, previously, we were talking about how to identify which device is issuing the interrupt. Now, for this guy, the interrupt controller, it will help us determine which goes first. So it accepts interrupt requests from attached modules, determines which interrupt has the highest priority, and then signals the processor by raising the interrupt request line, INTR, the interrupt request line. The processor acknowledges via the interrupt acknowledge line, INTA. This prompts the controller to place the appropriate vector information on the data bus. The processor can then proceed to process the interrupt and communicate directly with the IO module to read or write. So the controller, what it does is that it determines which interrupt has the highest priority if we are receiving multiple interrupts at the same time. And then it does so by going through the INTR request line. And then the processor will let the controller know by the INTA line. So here you can see that we have the controller, we have IR0 up until 7, which means that we have 8 lines here. 8 lines, which means that 8 external devices can be connected to a controller. And if we have more devices, then this would be cascaded to a master interrupt controller. So here, this is 82659A. This is also 82659A, but it is just cascaded like this. So you have your 8 here, your 8 over here, your 8 over here, and this is connected to the lines of the master interrupt controller. They are basically the same. The way that they are placed determines whether they are the slave or the master. Okay, so you know that the controller request using INTR, right? So here is the request line, INTR line, it goes to the processor. But in this diagram, they do not show the INTA, which is the line where the processor acknowledges the interrupt. So it should be like this. Okay, INTA, but it's not here, but it is there. Okay. So what else do we need to talk about here? This is, so if you only have 8, then you don't need this part. Then this would be directly to your processor. Okay. So if you have more, then you would do this in cascade where everything is connected to your master. And your if one controller can handle 8, so 8 times 8, you would have 64 altogether if you are utilizing all of the lines. Okay. Okay, so that is one technique whereby we use a controller to determine the priority of the interrupt. Now, the controller that we talked about just now is programmable via a control register. So you can, any questions? Hazmi, ada soalan? Tak ada? Okay, so I'm going to mute you, okay? Right, so if you have any question, you can unmute yourself and ask. If not, I'm going to mute you back if you accidentally unmuted yourself. Okay, so the controller is programmable, meaning to say what we talked about just now. This guy over here, you can actually control it via its control register. Inside this guy, you have your control register, which lets you set the mode of how you want to handle the interrupt. So the controller is programmable via the control register. You have a fully nested mode, you have a rotating mode, and you have a special mask mode. So the fully nested mode in this case is the interrupt requests are ordered in priority from 0 through 7. So IR0, this should be 8. Oh, sorry, it starts from 0, not from 1. Sorry, yeah, it is 7. So 0 to 7. So it seems like it's in order, but it's still called fully nested. We don't have sequential here. So fully nested looks like it processes the interrupt in order based on, over here, we have the 0 up until 7. So it processes according to this order. But it's called fully nested. I don't know the name, why it's named like that. Okay, so the second one, the second mode is called rotating. In this mode, a device after being serviced receives the lowest priority in the group. Let's say we don't use the fully nested, right? We have received multiple interrupts. Let's say I say, okay, I want to process this device first. And then even though this device has a high priority before, after it has been serviced, if the interrupt comes from device number 7 again, it would still be considered as low priority, even though typically it would be considered high. Because on the rotation basis or rotating mode, whatever that has been serviced will be immediately considered as the lowest priority in the group. So I'm not going to look at you until you have served your time, something like that. Okay, and then you have your special mask, the third mode. This allows the processor to inhibit interrupts from certain devices. So basically, I don't want to handle any interrupts from my phone. I disable by using the special mask mode. So sometimes you have like pop-ups, right? And you want to disable the pop-up, you can disable that. So that is like special mask. And in this case, you are masking that device, even though it is sending you interrupts, you mask it so you won't get interrupted. Okay. So what are the drawbacks of programmed and interrupt-driven I/O before we go into DMA? So we are concluding our program and interrupt-driven I/O. We have not talked about DMA, right? Or one yet. Okay, so both forms of I/O suffer from two inherent drawbacks. The first one is the I/O transfer rate is limited by the speed with which the processor can test and service a device. So remember, the processor has to test whether the interrupt is still there when it receives the interrupt, right? And after it is testing, it has tested the interrupt is still there. The interrupt is there, it has to acknowledge, and then it has to do the service. Basically, there was a software poll or a hardware poll whereby we had the interrupt service routine or device service routine. And then the processor is also tied up in managing the I/O transfer. So a number of instructions must be executed for each I/O transfer. Basically, you had to complete everything before you can go to the next instruction. How do I see this? Let's go back to the flow chart to make you understand this better. Not this one. Not this one. I can't see. I think it was this one. Okay, so remember that you had to like continue doing this until everything was done and then go to the next instruction. This is what it means, even though the sentence is quite confusing. Okay, so we are over here. Okay, so again, the first one is the transfer rate is limited by the speed at which the processor can do the testing and the servicing. Of course, if the processor is always busy, then you can't fully utilize the processor as well. By fully utilize, meaning to say speed things up. And then number two, the processor is tied up in managing and the I/O transfer. It has to finish all the I/O transfer before it can even think about doing something else. Okay. So those are the two inherent drawbacks. When large volumes of data are to be moved, a more efficient technique is the DMA. So you don't want it to be looped forever until, and then only it can process the next instruction. So if you have a lot of data to move around, you don't want it to be looped around for so long. What you do is you go for the DMA, which is a direct memory access. Okay, so I'm tired. Let's take a 5-minute break before we finish up the DMA. Hopefully we can finish it up. 5-minute break, 3:40 please. Let's come back. I'm tired. I need water. Okay, welcome back. Wake up. Let's continue our last 20 minutes. I realize that I don't have a teaching stamina like other lecturers. I get easily tired. Okay, let's continue. So now we are talking about DMA module diagram. So this is our typical DMA block diagram where we have the data count, the data register, the address register, and then we have our control logic, where the control logic handles requests to DMA. Of course, it goes into and acknowledge from DMA, goes out, and then the DMA will issue interrupt. So this goes out, and any reading will go through the DMA because the request will come from the processor, and any write will also come from the processor as well into the DMA. So all of that goes into the control logic. So the address register handles the data and also the address because the data has to be associated with some address. And the data lines are associated to the data count and the data register. So if you try to understand it, I think it's not too bad to memorize it. Okay, so the DMA involves an additional module on the system bus. So we know that the system bus handles the memory module, the processor module, the IO module, and now if we are implementing the DMA, we would have the DMA module as well. So the DMA module is capable of mimicking the processor, which is why it can take over the control of the system. It needs to do this to transfer data to and from the memory over the system bus. So basically it has to act like a processor. For this purpose, the DMA module must use the bus only when the processor is not using it. So how does it know when the processor is not using it? So we will discuss this. Or it must force the processor to suspend operation temporarily. So it will force the processor, hey, stop whatever that you are doing, pause, and I will take over the bus. The latter technique is more common and is referred to as cycle stealing. Not a very nice word, but this is the name that they've given it because the DMA module is in fact stealing a bus, stealing a bus cycle, not an actual bus. Okay, so this is how it looks like in the time frame. So here your processor is basically doing a fetch instruction, decoding, fetch operand, execute instruction, store result, process interrupt, these things that we have seen in chapter 2, I believe. Basically, these are all processor cycles. And your DMA interrupt can happen within these, within each cycle. So but the processor has to finish one cycle before this break comes in. So if you notice, the breaks only come after one cycle is complete. Only happens after one cycle is complete over here. Or it happens before the cycle even starts. So the DMA breakpoints or the interrupt is issued due after the cycle is complete or before the cycle is complete. So when the DMA interrupts, basically it's telling the processor, stop what you're doing, pause. If it was supposed to do execute instruction next, it won't be able to do it because now the system bus is taken over by the DMA module. Okay, so the DMA module then transfers one word and returns control to the processor. So it does this in bits. It does whatever that it needs to do, basically transfer the data that is required, and then it lets the processor continue its operation. Note that this is not an interrupt where even though I keep calling it an interrupt, the processor does not save a context. Sorry, you cannot treat it like an interrupt. When we say interrupt, we have to store the PSW, we have to store the PC, we have to store the general registers onto the control stack. So we shouldn't call it the interrupt. We have to call it the DMA breakpoints. Okay, so the overall effect causes the processor to execute more slowly, but this is more efficient than the interrupt-driven I/O or programmed I/O, even though it causes the processor to pause. Okay, so that is how it's done. It's not an interrupt, it's a breakpoint. Okay, so these are alternative DMA configurations. So we have a single bus detached DMA, whereby our DMA is a detached module. We have our processor module, IO module, memory module, and you have your DMA module over here. This is a system bus. And then a different configuration would be you have your processor module, DMA module connected to an IO module, DMA module connected to an IO module, and this is your memory. So basically whatever interaction between the peripheral device, any data transfer happens between these two guys, whatever request goes through the DMA. Okay, and then you have your DMA connected to a series of IO modules. This is your processor module and your memory module. So in 7.13a, all modules share the system bus. And in 7.13b and c, the system bus that the DMA module shares with the processor and the memory is used by the DMA module only to exchange data with memory. Okay, so the exchange of data between the DMA and IO module takes place off the system bus. So this is like a separate system. The DMA only interacts with the memory and the processor because the IO is now only connected to the DMA. Okay. Okay, so this is a lot. Let's try to understand this. So this is the DMA usage of a system bus. What do we have here? We have our DMA chip, almost like our interrupt controller just now, right? But this is for DMA. So this is our 8237 DMA chip. Do you have to remember the name? No, but you have to know that this chip exists. So the DMA chip handles call requests. Basically, it gives call request to the CPU. This is HRQ call request. The legend is over here. And then we have the CPU acknowledging this request, hold, acknowledge through this line to the DMA chip. Okay, so this is between the CPU and the DMA module or the DMA chip. And then from the DMA module, we are connected to the main memory and the disk controller. So this is our IO peripheral device, disk controller. Okay, please read this as IO peripheral device, even though it's very ugly. Okay, so the request comes from the IO, the peripheral device. So it goes through the DREQ, which is the DMA request. It's requesting the DMA module to do something. Maybe read, maybe write, I don't know. And then the DMA module responds to this by acknowledging this DMA request. So DREQ is DMA request. DACK is DMA acknowledge. The DMA responds to this request by acknowledging it. And then it proceeds to go to the CPU and say, hey, I have a request, call request. And the CPU acknowledges this request, HLDA, I am acknowledging your request. Okay, so that is basically it. There's a lot of lines to confuse you, but basically it's just that. Okay, so the evolution of the IO function, we talked about the program IO. The CPU directly controls the peripheral device first, and then a controller or an IO module is added. We saw that earlier, a controller, and then same configuration as in step 2, but now interrupts are employed. So this is the evolution. And then number 4, the IO module is given direct access to the memory via the DMA. So this one happened first lah. Basically, you started with this, and then this is not good. We evolve to this, and then we evolve to the number 3, and then we go to the DMA module, which we discussed just now. So the coming ones are the IO module is enhanced to become a processor in its own right. Previously, the DMA acts like a processor, but now we are giving control to the IO to act like a processor in its own right. So with specialized instructions set tailored for the IO. And then the most advanced one in this book that we discussed is the IO module has a local memory of its own and in fact a computer in its own right. Okay, so this is our IO module. With this architecture, a large set of IO devices can be controlled with minimal CPU involvement. So our IO has a brain of its own, which is great. Okay, so let's discuss that. Have we seen that? Do we know an example of that? So actually we do have an example of that, which is It's not this one, but okay, let's discuss this one first. So there are two I/O channel architectures. So the I/O channel represents an extension of the DMA concept. You know that the DMA is basically a module given the rights like a processor when there is a large amount of data that needs to be transferred back and forth. So it handles that and has the breakpoints that basically tells the CPU to pause its process, right? Okay, so after that, we have the I/O channel architecture, which is an extension of the DMA. Basically, we are trying to discuss the advancement of the I/O channel, basically. Okay, so there are two types. The first one is the selector. The second one is the multiplexer. The selector is basically controls multiple high-speed devices at any one time because it selects which one it wants to entertain. Is dedicated to the transfer of data with only one of those devices. Whereas for multiplexer, you handle multiple devices at a time. For low-speed devices, this is ideal. A byte multiplexer accepts or transmits as fast as possible to the multiple devices. So the name is straightforward. You have a selector or a multiplexer. A selector, you select one. You do basically for a high-speed device. A multiplexer, you handle multiple devices at a time for data transmission back and forth. Okay, and then we have the parallel and serial I/O. So in a parallel interface, there are multiple lines, of course. And for a serial, you have one. So serial interface used for slower speed peripherals, basically like a printer. I keep using printer because it is slow. And then for this one, if we want to handle a high speed device, basically you want a lot of data to go through. Okay, so you have two types, parallel and serial. And then we have point-to-point and multi-point configuration. So what is point-to-point? Almost like the same thing that we discussed just now, serial, but provides a dedicated line between the I/O module and the external device, almost like a selector and serial. And then multi-point external interfaces are used to support external mass storage devices, multimedia devices, whereby these are high-speed devices, right? So are in effect external buses. Okay, so I'm just going over these. Okay, so this is one of the peripheral connection technology. I don't know if you know what Thunderbolt is. Don't know if you've used this. I think you have if you have an iPhone. After Thunderbolt, they called it Lightning Port. Previously, it was called Thunderbolt, if I'm not mistaken. So Thunderbolt is a peripheral connection technology or an I/O connection technology. So it was the fastest peripheral connection technology to become available for general purpose use in 2011. So basically Apple came through with this new technology. The speed was great. And why they wanted to do this is because they wanted to dominate the market for their own ecosystem. They didn't want like OEM to like to bug their market or like to invade their market. They wanted a market of their own, which is why they have like a unique port for all their devices. So basically they want to monopolize everything within their system. Okay, so developed by Intel with the collaboration of Apple, the technology combines data, video, audio, and power into a single high-speed connection for peripherals such as hard drives, RAID arrays, video capture boxes, network interfaces. These are all very high-speed devices. Provides up to 10 gigabits per second throughput in each direction. So at that point, in 2011, that was like the thing, right? So a Thunderbolt compatible peripheral interface is considerably more complex than your simple USB. So if you were to use your Windows, the USB would be slower compared to a Thunderbolt. So, you know, the Apple people were like, hey, my computer is faster than yours, blah, blah, blah. You had that thing going on previously, but now it's almost on par. So Apple does not have that going for them now. And do I have a chat going on? I thought I saw someone typing in, but I can't read it. Should check. Well, I can't read it. I don't know why. Okay, moving on. Thunderbolt was a standard feature of Apple's MacBook Pro laptop and iMac desktop computers. Okay, let me justify myself why I use a Mac. I'm not trying to like tell you guys I have a good computer. Why I use Mac? Why am I justifying myself? I don't know. Okay, so basically why I use Mac is because this is already my 4th year using it and it still feels new to me. I've not upgraded to M1. So this is why I go for Mac. My Windows doesn't last very long, but in terms of technology, I admit Intel has it stronger, is stronger in the department compared to Apple. But in terms of stability, Mac is very stable. Okay. Okay, continuing, computer configuration with Thunderbolt. Let's not go through this. Yeah, let's not. And then we have the Thunderbolt protocol layers, not important for our class. And then after the Thunderbolt, we had InfiniBand, which was another, how do I say this? Another peripheral connection technology. So it enables servers, remote storage, other network devices, very, very fast. The switch-based architecture can connect up to 64,000 servers, storage systems, and networking devices. So not basically for end users like us at that time. So maybe you are not really familiar with this name. Okay, but it is a very good technology at that time. And then this is the switch fabric. I'm just exposing you to this name. We have the Thunderbolt, the InfiniBand. And then we have, of course, protocol layers. As with any complex systems, we do have the protocol layers. And then this is the communication protocol stack. I'm not going to discuss this one. And then, no, not this one. Okay, so this is an I/O system organization, just showing it to you guys. Don't have to memorize this, just exposing. If we could like go to a company that has all these things, it would be fun, right? But even if we can see it, it's not very interesting to look at these things, right? So even if I bring you to a class trip, the fun part would be the walking part, not really looking at this thing. Betul tak? Okay, and then we have this, not discussing this one, and we are done with chapter 7. So for the ones that I glossed over, what you need to do is, what are the examples of peripheral connection technology? You had the InfiniBand, the Thunderbolt. If you can find other examples from your own reading, that's great too. Okay, so that is it for chapter 7. I will be assigning your homework again, but I will let you know when it is up on Putra Blast. Okay, so take care, everyone. Have a great rest of the day. If you have any questions, you can ask me now. If not, you're free to go. Thunderbolt supports 40 gigabit per second now. That's cool. Okay, bye-bye. Bye, everyone. Welcome. Welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Doctor.
Welcome.